In this fourth lecture of third chapter, I shall discuss first occurrence of metals, second extraction of metals. First I discuss occurrence of metals. Most of the metals being reactive are found in combined state. Only a very few metals which are very less reactive, for example copper and gold, are found in native or uncombined state. Metal compounds are also mixed with other substances or impurities. These substances are called gangue. A naturally occurring material from which a metal can be economically extracted is called an ore. A metal can be extracted from more than one ores. Next, I discuss how the metals are extracted from the ores. You know that the reactivity of the metals varies. The list of metals written in order of their decreasing reactivity is called reactivity series. To get a metal from its compound, it should be reduced. The reduction process adopted depends on the reactivity of the metals. For that, metals are put under three groups. First, metals at the top of reactivity series, for example all S block or first and second group metals, and some of P block metals also. Second, metals in the middle of reactivity series, for example most of the D and P block metals like zinc, iron and lead. And third are the metals that lie at the bottom of the reactivity series. For example, copper, silver, gold and platinum. The first step in extraction of metals is called concentration of ore. All materials other than the ore are called gangue. In this process, gangue is removed from the ore. After concentration, the process adopted for the extraction of metals depends on the reactivity of the metal. High reactivity metals are reduced by electrolysis of the molten ore or ore mix in appropriate molten electrolyte. In electrolysis, selection of appropriate electrodes, the temperature and EMF applied are very important. Extraction of metals other than those on the top of the reactivity series, the ore is first converted into an oxide if it is other than the oxide. Some metal ores are carbonates. Most of the metal carbonates are not much stable to heat. They are heated in absence of air to decompose into carbon dioxide and metal oxide. This process of heating an ore in absence of air is called calcination. Metal sulfide ores can be converted into metal oxides by heating in presence of air so that both metal and sulfur react with the oxygen present in the air to form oxides. Heating an ore in the supply of air or in presence of air is termed as roasting. Reduction of some of metal oxides low on reactivity series can be done just by heating because those may not be stable to heat. Reduction of oxides of metals low on reactivity series may be just done by heating because their oxides are not so stable to heat. Mercury is found as mercury sulfide or HGS, which is first roasted. The reaction is HGS plus O2 produce HGO plus SO2. HGO produced like this can be decomposed simply by heating up to 400 degrees Celsius. Similarly, CuS is roasted to convert partially into its oxide and then calcined. The reactions are Cu2S plus O2. On being heated, produce Cu2O plus SO2. And the second reaction, Cu2O plus Cu2S, produce Cu plus SO2. Reaction of metals in the middle of reactivity series. Generally, these metal ores are sulfides, carbonates, and oxides. Sulfides are first converted to oxides by roasting and carbonates to oxides by calcination. For example, zinc sulfide or ZNS plus O2 on roasting produce ZNO plus SO2. And zinc carbonate or ZnCO3 on calcination produces ZNO plus CO2. Metal oxides so obtained can be reduced to metal by reduction with carbon or reaction with highly reactive metals or with hydrogen. Carbon is the cheapest element and thermodynamically suitable to reduce most of the oxides at a reasonable temperature. Therefore, it is widely used in reduction of oxides into metals. For example, ZNO plus C on being heated produce zinc and carbon dioxide. Reactive metals like sodium, potassium and aluminium or calcium can also be used to displace less reactive metals. For example, aluminium can reduce a zinc oxide or manganese dioxide. The reaction is MnO2 plus Al or aluminium produce manganese plus Al2O3 or aluminium oxide and heat is evolved. It is an exothermic process. And Fe2O3 plus aluminium produce Fe or iron plus Al2O3 or aluminium oxide. Though initially heating is required, once the reaction starts, the reaction temperature is maintained by the heat evolved in the reaction. Now the question arises, can carbon be used for reduction of highly reactive metals? Explain. Electrolysis is expensive process. Now the question is, why can carbon be not used to reduce their oxides? Theoretically, carbon can reduce oxides of almost all metals, but 2 points make it unsuitable for highly reactive metals. First point is the temperature required is too high, that creates many practical problems. And second point is that at very high temperatures, metals form carbides. In the end, I summarize this lecture. Most of the metals are found in nature in the form of their compounds or complexes mixed with other materials. These other materials are called gangue. An O is naturally occurring material from which a metal can be economically extracted. The first step in extraction of metals is concentration of O. Minimizing of gangue in the O is called concentration of O. The second process is decomposing or displacing the metal to be extracted in its compound. The method of reduction adopted depends on the reactivity of the metal. Least reactive metal compounds are first converted into oxides and then those oxides are decomposed by heating. For example, mercury and copper are extracted like this. Medium reactivity metals like zinc and iron are first converted into their oxides by calcination and roasting. And then the metal oxides are heated with carbon to get the metal. Means carbon is used as a reducing agent here. Highly reactive metals like first and second group metals are extracted by electrolysis of their molten salts or other suitable molten salt. Here is a question for you. Which reduction method can be applied for extraction of any metal irrespective of its reactivity, and why? And that's it, the fourth lecture. This chapter will be continued in fifth lecture. Till then, goodbye.